So what we have in question 81 is we have a spring that's attached at one end to a wall, and the other end of the spring is attached to a block of mass m. And we're not actually told that mass, but I'll just give it a symbol anyway. I'll call it m. And then what has happened is that someone has come along and stretched out that spring. And so the spring has been displaced a distance xi away from its equilibrium position. And we're actually told what that distance is. We're told that xi is going to be 0.05 meters. So the spring is 0.05 meters longer than its relaxed length. And then what's happened is that the person who stretched the spring, in addition to letting that block go, they also give it a push. They give it a push so that it leaves this position here with an initial velocity of what they call VO. Back that way. And the question is asking us to figure out what this VO has to be in order that after the block has travelled all the way this way and come to a momentary rest and then started moving back this way again, we want to know how fast the initial speed has to be such that the block travels all the way out here to a new position xf, which is 0.08 meters away from this equilibrium position. And so the initial speed is just this VO, which we need to calculate, and the final speed of the block when it gets over to here is 0 meters per second. And according to the question, there is also a bottle here, which means that if the block can just come to rest at this point here, then it will just narrowly avoid knocking the bottle over. So we need to figure out what the initial speed of the block has to be in order for this to be the case. So probably a good place to start would be to note that, well, really, there is only one force acting on this block after it's released, and that is the spring force. So gravity also acts on the block after it's released, but that is always perpendicular to the motion, so that can't do any work. Friction doesn't do any work either, because we know that this surface here is frictionless. So in that case, since only the spring force does work on the block, that means that the net work being done on that block is just equal to the work being done by the spring force. And the net work by the work kinetic energy theorem is just equal to the change in that block's kinetic energy. And this is probably going to be a useful relationship because this change in kinetic energy will involve this speed here and the speed of the block once it arrives over to here. And so it will give us an equation for this speed here that we hopefully can solve. So let's think about, well, what is the work being done by the spring force? As usual, this is equal to the negative of the change in the block spring system's elastic potential energy. And the change in the kinetic energy is just going to be equal to the final kinetic energy. So the speed over here, so the speed of the block when it gets to xf is 0 meters per second. So that means its final kinetic energy is going to be 0. So the change in kinetic energy is going to be 0 minus the initial kinetic energy, which we know has to be a half mVo squared. Now the change in the elastic potential energy is going to be the final elastic potential energy, which is just a half kxf squared minus the initial elastic potential energy, which is a half kxi squared, and that's going to just be equal to a half mVo squared. Now here I see that both of these terms have a common factor of a half k, so we can just factor this out and pull it outside the brackets. And we can also cancel out these minus signs, so let's just tidy this up a little bit. So this is going to be xi squared minus xf squared is equal to minus a half mv naught squared. And here we see that both sides of this equation have a common factor of a half, and we can also cancel out minus signs again. So this is going to be given by k, xf squared minus xi squared is equal to mVo squared. And perhaps we should note that where k is the spring constant. Which unfortunately we don't know. However, something that we do know is that when the block and the spring are set into simple harmonic motion, the angular frequency of that motion is 7 radians per second, so we know that. And we also have a formula that relates angular frequency to the mass of the block and to the spring constant, and is this. So we know that where omega is 7 radians per second. So we can now solve this equation for the spring constant. So here, if we just square both sides to get rid of the square root, we're going to have that omega squared is k divided by m. And to solve for k, then we just need to multiply both sides by m, and we get this as m omega squared. Now we don't know the mass either, but fortunately, this side of the equation here has a factor of the mass as well. So it seems to me that when we plug this into here, those two masses will just cancel. And so that should work out nicely. So if we just call this equation star, we can say plug into star. And what we get from doing that is we find that the mass times the angular frequency squared times the difference in the initial and final positions, or the square of the initial and final positions, is given by mVo squared. And so our mass of the block appears on both sides, so we can cancel that out. And then finally, to solve for this VO, so the initial speed that the block has to be given, we can just take the square root of both sides. And so when we do that, we get to this. And just before we go, we see that there's a common factor of omega squared that's being square rooted, so we can just pull that outside of the square root. And we'll have this instead. And now if we plug the numbers in, we know that the angular frequency is 7, and now we just multiply that by the square root of xf squared, so 0.08 squared, take away 0.05 squared, and we find that the initial speed that the block has to be given will be 0.437 meters per second. If it's given an initial speed that's anything greater than that, then it won't come to rest here, but it will go a little bit further, and if it goes a little bit further, then it will end up knocking the bottle over.